From our previous video, we know that thermodynamic favorability is the property of a chemical process to continue on its own without additional intervention needed to continue on. But how do we predict if a reaction is thermodynamically favorable or not? It turns out there's an equation, and the equation is known as the Gibbs free energy equation. It is delta G naught, which we're going to call the Gibbs free energy, which we'll define that a little better here in just a moment, is going to be equal to the delta H, which is the change in enthalpy, remember, which we learned how to calculate earlier in the semester, minus the temperature times the change in entropy, which we just discussed. All right. One thing to note, the T here, the temperature, is the temperature always in Kelvin, never in Celsius. So this number is always going to be positive. Just remember to change everything into Kelvin by adding 273 to the Celsius value. All right. Now, why do we want to do this? It turns out that the Gibbs free energy is a predictor of whether or not a process is thermodynamically favorable or not. If the delta G value is less than 0, in other words, it's negative, the process will be found to be thermodynamically favorable. However, if the delta G value is found to be positive, the process is going to be found to be thermodynamically unfavorable and therefore unable to occur without intervention from an outside source. So let's do an example of using the equation to predict favorability. And so what you do is you always just go look up the values, or you calculate them using all the methods that we've learned so far how to do that, all right? And so let's say you do that for a reaction such as the burning of propane. All right, and so if we go look up the values, or we calculate the values for delta H and delta S, we get that delta H for this process is minus 2202 kilojoules per mole. And the delta S for this process is going to be positive 103 joules per mole Kelvin. All right, let's say we ask the question, is this process thermodynamically favorable at room temperature, 25°C. All right. I will mention before we even do the calculation, this is the burning of propane. We're taking propane and we are reacting it with oxygen. Remember, that's just burning or combustion. You know for a fact that if you light some propane on fire, it will continue on without additional outside intervention. So you know just from your personal experience, at least I hope, that propane burning is going to be thermodynamically favorable. So we should get a negative delta G out of this, but let's see. So we're going to plug in to the Gibbs free energy equation. Incidentally, these little knots up here, we're going to discuss those in more detail later on when they are not there. This is assuming that all your solutions are 1 molar and all your gases are 1 atmosphere. It's a technical issue that is going to be more obvious when we take them away. So for now, just write them and understand we're going to talk more about those later. All right, so the delta G naught is going to be equal to minus 2202 kilojoules per mole minus, remember to change your 25 Celsius into Kelvin. So that's 298 Kelvin. We have a delta S of 103 joules per mole Kelvin. Kelvin are going to cancel. Now we're going to run into a problem here in a moment, which is that we have joules here and we have kilojoules over here, right? And so we're going to have to get those to be consistent with one another. And the way that we're going to do that most of the time is we're going to divide this guy by 1,000 and turn this into kilojoules. I'm just going to do that right now. Move the decimal place 1, 2, 3 times. Put a decimal there. This now is kilojoules, and that's going to make everything add correctly. All right. Remember that to add two numbers together, they have to have the same units. This is now going to be kilojoules over moles. Everything's good. So we get 2202 kilojoules per mole minus 298 times 0.103. 30 point, we're going to round that off at 3 significant digits, so that's going to be 7, and that's going to be kilojoules per mole. All right. Notice here that this negative sign out here applies to this whole expression here. So sometimes there's going to be a negative sign out here, which is going to change this into a positive. But here you have a negative in front of a positive and a positive. So the answer is just negative. All right. So we're going to add those together. And our delta G naught here is going to be negative 2233 kilojoules per mole. And so, in fact, because delta G naught is less than 0, in other words, it's negative, we're going to conclude that this process is thermodynamically favorable. Later on, we're going to have a use for this, the actual numerical answer here, but for right now, all we're doing is stating whether a process is favorable or not. So we know, because the delta G is negative, that this process is going to continue on its own without the need for additional outside intervention once it is initiated. You're allowed to initiate it, remember. You're allowed to strike a match and get this thing burning, but once a propane source is burning, it is going to continue on without the need for additional outside intervention, as is demonstrated by the negative delta G value.